Welcome to a Mech and Chips video. This video will explore photonics, delving into the magnificent physics behind the time-of-flight sensors that allow us to detect distance and speed of moving objects. We will strive to bridge the gap between the physics and engineering in this field by combining the explanations with an appropriate project which demonstrates the function of LiDAR time-of-flight sensors. The project will utilize the functionality of both VCSELs and SPAD photonic devices within an electronic setting to create a speed sensor by measuring changes in distance. Laser diodes must transmit coherent and collimated light. One method of doing so is by using a vertical cavity surface-emitting laser, or a VCSEL as it is more commonly known. These are structures with two Bragg reflectors above and below a semiconductor active region, which is where the lasing or generation of light will actually occur. The oxide contact on the top is circular, so that any light that is transmitted through the upper Bragg reflector is emitted in a circular and straight pattern. To initially emit a photon, the electrons of the semiconductor compound in the active region will have to be excited and reach a higher energy state. This helps to achieve population inversion, which is where all of the electrons in the active region are forced into excitation, making them ready for stimulated emission. However, electrons in the semiconductor do not usually remain in the higher energy level for long enough to be stimulated, as these energy levels are unstable. This means the electron falls back to the lower energy level, releasing a single photon through spontaneous emission. To help, we use metastable energy levels. These are more stable energy levels, close to the highest energy level, and thus the electron is able to remain excited for longer, ranging up to a few milliseconds. This helps to achieve stimulated emission. The spontaneously emitted photons from other atoms will interact with the metastable electrons and push them down to the ground state again. As the electron falls, it will release photons with energy equal to the difference in energy levels, which is also proportional to the frequency of light emitted. The mirrors present in the VCSEL are Bragg reflectors used to generate incredibly high reflectivity. These are formed by placing nanoscale layers with increasing refractive indexes, which consist of many internal interfaces. The thickness of each is equal to a quarter of the wavelength that needs to be selected. This will result in the path difference equaling half of the wavelength after the light reflects off one of the Bragg interfaces. While this would mean destructive interference with the original wave in a regular interference scenario, the pi phase shift on reflection at an interface makes this path difference constructive when it interferes with the original light wave. Note, in a VCSEL, the top Bragg reflector has somewhat of a lower reflectivity. This allows some of the coherent and collimated light from the cavity to pass through and be emitted from the surface. This process is part of the laser's resonator. When the reflected light passes over the active region again, it interferes with the excited electrons again. This creates an avalanche of photons, which are also emitted and travel alongside the original light, which increases the brightness. These waves then form a stationary wave of select frequency within the resonator, defined by the length of the cavity. This creates a range of possible frequencies of light that could be emitted. However, only the frequency matching that of both the band gap of the medium and the resonator is selected. One method of detecting incoming light is by using a SPAD array. SPAD stands for Single Photon Avalanche Diode. These are PN arrays that rely on individual photons to strike the diode to create an electron-hole pair. By connecting the voltage supply to the PN diode with a reverse bias, we can obtain a large depletion region. A photon is absorbed and creates an electron-hole pair in this depletion region. This creates a free electron, which is then accelerated by the strong electric field of the voltage in reverse bias. This then collides with other atoms in the depletion region, allowing for even more free electrons, as the kinetic energy of each electron after the collision is sufficient to knock off an electron from the atom. The ratio for this positive feedback is one colliding electron to two free electrons in the conduction band after the collision. This continuously occurs until an avalanche of free electrons reach the cathode and a very rapid and strong current is onset, which can reach up to a couple of milliamps.